In this lesson, we're going to finish off section 6.4 and talk about the electrochemical cell. And this time we're going to talk about two different types of spontaneous reactions. We're going to explain what happens in an electrochemical cell when we reach equilibrium, what happens there. We'll look at some common types of batteries. And then the second thing that we're going to look at in this is a spontaneous reaction that causes corrosion to occur and how we can actually prevent this. You can see down at the bottom there that there are a number of different types of examples of batteries. And we're going to go through three different types of electrochemical cells. We'll look at alkaline dry cells, lead acid storage batteries that are used in vehicles, and then finally we'll look at fuel cells. Now, first, before we get into the different types of batteries, we're going to talk about equilibrium in electrochemical cells. If you remember from our equilibrium discussions in the previous three chapters, when we're reaching equilibrium, we have no major changes that we can observe through the human eye. So macroscopic changes don't occur. When we look at electric potential of a cell, we are assuming standard conditions. However, those conditions do change as the cell operates. And what happens over time is the voltage of that electrochemical cell drops. As the cell operates, those electrons are being transferred from the anode to the cathode, and consequently, the species in the cathode gets better at donating electrons, and the species in the anode gets less proficient at donating electrons. When the species in both the anode and the cathode are equally proficient, that's what we call cell equilibrium. So that's when we observe a dead battery. It's not the same thing as dynamic equilibrium, but we call it cell equilibrium because we observe no major changes and basically the battery is effectively dead. So different than a dynamic equilibrium, but we're still talking about something in balance. In terms of the different types of batteries, we've got three main types that we're going to look at. The first is alkaline dry cells, and these are your typical Energizer or Duracell. It's an electrochemical cell, several of them, where we've got usually a zinc powder and a brass pin, and then a paste of manganese dioxide and powdered carbon that's helping them work properly. In there, we have an electrolyte as a potassium hydroxide paste. So you might see some of this calcium hydroxide if you ever have a battery burst, like if you leave a battery that is in equilibrium inside an object after it's already at equilibrium. The two half reactions that are taking place are between the manganese dioxide in the cathode and the zinc and in the anode. And you'll notice that the anode reaction there is in basic conditions. We're actually balancing that one with hydroxide there. Cathode, that manganese dioxide turns into dimanganese trioxide, and we get that basic condition as well. The way that the batteries are set up is we kind of have this loop set up. So we've got the anode right in the middle, and that brass pin is acting as a current collector. So that's what the brass pin does. And then we have a separator that separates the manganese dioxide from that as well with the cathode. The second main type of battery is a lead acid storage battery. So rather than being in a basic condition like the potassium hydroxide that we see in the other batteries, these lead acid storage batteries are taking place in an acidic solution. And so that's where hydrochloric acid comes from, or sorry, sulfuric acid is coming into play. So what we have with a lead acid storage battery is we have 6 cells that are actually connected in series. So each of those 6 cells produces 2 volts of electricity. When we connect them in series, we add that up to 12. The anodes for this are a lead alloy, and then we have grids with spongy lead as well. So the lead reacts with the sulfuric acid, or hydrogen sulfate, and creates lead sulfate. And at the cathode, we have lead 4 oxide that reacts with the sulfuric acid as well and creates lead 2 sulfate. The electrolyte in this is an aqueous sulfuric acid that allows those cations and anions to complete the circuit. You can see the setup of those 6 interconnected cells in the pictures there. The last type that we have here is a fuel cell. So with fuel cells, the difference between these and the other types of batteries is that the reactants are continually resupplied from an outside source. And therefore, these ones don't reach that equilibrium because we have hydrogen being oxidized at the anode, oxygen being reduced at the cathode. Both of the electrodes are porous carbon, and I'll put a video up of this where we can actually have hydrogen and oxygen gases being produced through this. And with the electrodes, we have them bonded to a proton exchange material. So that's coated with a thin layer of platinum, and that platinum acts as a catalyst for the reaction. You can see the two reactions taking place there. So the oxidation reaction is the hydrogen losing the electrons. Those electrons are then picked up by the oxygen, and that oxygen reacts with hydrogen to become water. So that's how a hydrogen fuel cell works. There's been a lot of research done into these hydrogen fuel cells, and people are trying to look at how we can harness the hydrogen fuel cell as a potential means for transportation. Some of the drawbacks to this is if we're going to gather hydrogen and gather oxygen for these reactions to take place, then that requires electricity as well. So it's kind of, when are we generating this electricity and what source is it coming from that has been the hold up of this as well. And one of the other problems is that because it's generating water, we have to be very careful that it's not just generating water vapor, because water vapor is a greenhouse gas as well. The last thing that we're going to talk about in this lesson is corrosion. And corrosion is when we have oxidation of a metal that we're not meaning to have. And if you were ever a kid riding a bike and you left your bike out in the rain, you might have found out that corrosion takes place quite quickly. Rusting is oxidation of iron specifically, and that's where we actually get rust from. So we're going to go through the equations and how rust occurs, and then talk about how we can prevent corrosion from taking place. So first off, here's a diagram of what is actually taking place when we're getting rust. And we're going to start over here, kind of at the edge of our water droplet. So you can see that kind of blue section behind there. That is a droplet of water. And for these reactions to take place, we have to separate the half reactions. So we have that water that is helping transfer of electrons and helping those reactions take place. Oxidation takes place in the center of the water droplet where there is no oxygen. And then electrons will transfer and travel through the iron metal to the oxygen molecules at the edge of the droplet. So what happens is those electrons get donated from the iron. Iron becomes iron 2+. The electrons get transferred to the oxygen. Oxygen picks them up, mixes with hydrogens from the water, and becomes liquid water. The last step here is that iron 2+ is further oxidized. So we don't just have this kind of blue water droplet sitting on top of your bike chain. That iron 2+ is further oxidized to iron 3+ when it reacts with dissolved oxygen. And then that iron 3+ goes on to react with oxygen further and forms that Fe2O3 mixed with water. And that's actually what rust is. So what we're going to talk about is, because we know we have this reaction taking place, how do we actually prevent it? And there's two different ways that we can prevent corrosion. The first way to prevent corrosion is to prevent the reactants from coming in contact with one another. So with this, what we're actually trying to do is to stop those water droplets from forming, because if you stop the water droplets from forming, then you don't have any of the electrons being able to be transferred between the iron and the oxygen. So that's one way that we can prevent the corrosion from taking place. This one's an easy and pretty cheap way of preventing corrosion from taking place. We can use paint, and so that's what you can see there with the steel bars being coated with paint, or we can coat with plastic. So a lot of your electronics that you'll buy, you'll get those kind of plastic coverings covering things, particularly with metal. That's preventing any sort of oxidation to take place, and it keeps your metal shinier and is a really cheap way of doing that. The second way of preventing corrosion from taking place is a little bit more chemistry intense, and it's implying a cathodic protection. So what we can use for this is a sacrificial metal, for example. And those sacrificial metal is attached to the metal that you're protecting. Now this has to do with our standard reduction table because some metals are more reactive than others. So if you take a look at your standard reduction table, you can kind of see the chart on the right-hand side. You can see that our most reactive metals are sodium and calcium and magnesium. Then we get into the ones like aluminum, zinc, iron, tin, lead, etc. Most of the things that we have made around the world are kind of hybrids of iron. And so what we want to do is we want to find a metal that is more reactive than the iron that we can use as a sacrificial metal. We have to have a metal that will be better at donating those electrons so that the oxidizing agent will take that away rather than taking away the iron. Now, sodium, calcium, and magnesium, sodium and calcium in particular, are really, really bad choices for metals, and that's because they react with water. So if you stick sodium in water, it will spontaneously react. It's way too reactive. So we have to find something that's a little less reactive than that. And usually zinc is the one of choice for picking a sacrificial metal. So you can see there a couple of examples. If you take a look at the hull of that boat, those chunks of metal that are attached to the hull there are not any mistake. Those are actually zinc bars that are welded to the iron steel ship hull. And the zinc, because it's better at donating the electrons, those electrons will get donated and go into the steel because they're metals, so the electrons go between both very easily. And those zinc bars will eventually degrade and have to be replaced, but the steel hull won't rust in the meantime. Another way where we can use zinc is with coating metal with zinc by galvanizing it. So you can see the little nail over on the left-hand side there. The zinc oxidizes and forms zinc oxide, and that forms a protective layer on top of the nail that stops it from rusting. So if you buy galvanized nails or galvanized screws and things, that's what it's actually doing. It's providing that sacrificial metal that will stop and form a protective layer so it doesn't rust as easily. Here's a last example of how a sacrificial metal can be used. And in this one, it is protecting a steel pipeline from corrosion. So with this one, buried underneath the soil, we can bury a magnesium rod, connect it to that steel pipeline. And because we've got kind of moist soil there, what we're going to be doing is the electrons from the magnesium are going to be transferred over to the steel pipeline. That sacrificial anode of magnesium will start to be used up, but it will protect that pipeline from rusting. And so that steel pipeline won't get rusted through, and then we don't have to worry so much about it bursting and environmental disasters. So I hope this lesson kind of showed you some practical uses of electrochemistry, and please answer some of the questions in the textbook and let me know if you have questions. Thanks for watching.